Hi, I am making these two short videos to go over some past problems that might accurately reflect what problems on your final look like. So in this video I'm going to go through a couple of multiple choice questions on magnetism, and then in the second video I'm going to go through two long answer questions. And these are taken from past exams. Of course those were not online, but you know, the physics hasn't changed. So it's start number 19 because this was taken from an exam where there were other topics on the final as well. Right, the structure was a little bit different across the course, but this is the relevant section to Phys. If the Earth's magnetic field were to be modeled as a giant bar magnet, its magnetic south pole would be somewhere underneath what? So two of those answers are obviously nonsense, namely C and D. Right? The Earth has poles, and it has the geographical north pole and geographical south pole. And the magnetic poles roughly correspond to those locations. So C and D are just, they're just total nonsense. But the question is, which way around is it? Is the magnetic south pole underneath the Arctic or the Antarctic? Now, of course, this requires you to know what the Arctic and the Antarctic is. So this is actually explained here, north of Canada somewhere or south of Australia somewhere, right? So it kind of tells you which one is north, which one is south. So I do sincerely hope that you knew that anyway. So which is it? The magnetic south pole. It turns out, if you watch the videos, if you've read the book, you know it is actually, the magnetic south pole is actually in the geographical north. And the magnetic north pole is in the geographical south. That's because a compass needle's north end was labeled that way because it pointed north. But compass needles point in such a way that the north pole of it points towards another magnet's south pole. Right, so this is why it ends up being flipped. I explained it in more detail in some other videos. The answer is A. 20. A copper ring rests on a table. A magnetic field points straight down to the surface of the table and is gradually decreasing. Is there a current induced in the ring, and if so, in what direction? So the answer is, well, there is a changing magnetic field, so there must be a current induced. Right, it is essentially Faraday's law. And the direction of it we're going to figure out with Lenz's law. Let me draw this. So I'm going to draw a ring. This is my ring sitting on a table. You can imagine that this side down here is closer to me, so I'm kind of looking down on it, right? So if I want to draw the table, just to make that a bit clearer, right? I'm going to draw the table. Might look sort of something like this. Right, this is my 3D sketch of a table. Right, you get the idea. So there's a copper ring, a magnetic field points down. Right, so the magnetic field points down. But the magnetic field is getting weaker. So if the magnetic field points down but it's getting weaker, then the change in magnetic field must point up, right? Because I have those, but later on I will have less of those, so it's a change that's up. A little bit like if you have velocity down, later on the velocity is less, well then the acceleration was up, right? That's the analogy that can help you make sense of this. So then Lenz's law states that the direction of the induced field, so the current gets created in the ring, and the direction of the magnetic field created by that current is going to be the opposite of the change of flux, the opposite of the light blue arrow here. So the magnetic field induced is the green one here. I'm not labeling this in the diagram. I'm talking about it, so you can keep your notes. So which way around is this? Well, this is meant to be, the arrow is meant to be like inside the loop, right in the middle of the loop. So you can use your right-hand curly rule to then figure out that to get a magnetic field pointing down, the current must be clockwise. The answer is clockwise. This one here. Number 21. Two parallel wires run across the table. One carries a current of 2 amp, the other current of 1 amp. Currents are in the same direction. What's true about the magnetic interaction between the two wires? Alright, let's draw this out too. Here we go. Here's one wire, here's a second wire, and we're going to assume that in both cases the current runs up. Now, whether or not it's attractive or repulsive, I mean, isn't changed by the amount of current. So that's really just there to, I wouldn't say confuse you by the 2 amps, 1 amp. It's just there. It's what we would need if we were worried about the strength. So how do I figure this out? Well, I can figure out, I take one of the wires and see what magnetic field it creates. Let's see if I can draw this. It's going to be a bit messy. This one is going to create a magnetic field that looks something like this. Right? And it goes behind the wire here, in front of it here. Kind of it comes out of the page and goes into the page, goes behind it. Of course, it also does this if you're further away from it. Something like this, right? And again, this should be behind it. I wasn't being very careful here. Right. So, what's this telling me then is that there's a magnetic field at this wire that points into the page. If I just draw this again, just draw again those 2 wires. Here's one, here's the other. Right. The wire on the left creates a magnetic field that is into the page over here and comes out of it over here. Comes out of the page, goes into the page, circles around. But we just care about what's the magnetic field where the other wire is. And in this case, it's into the page. Now you can use the right-hand rule, and your thumb goes upwards, right, with the current. Your index finger points inwards into the page with the magnetic field, and your middle finger should point to the left. So that tells you that the force is to the left. You do this the other way around, and you figure out that the force on this wire is to the right. So they're going to be attracting each other. Now, really, you only have to do it once, because by Newton's third law, right, the force in the other one has to be the other way. So it's the last two, they're not labeled C and D, should be labeled C and D, right? They're just total nonsense, because the force has to be in opposite directions, so it's either repulsive or attractive, but not sort of repelling one, attracting the other. It just doesn't make any sense. And the answer is that it's attractive, so it's the first one here, like this one right there. Alright, number 22. Magnetic braking is an effect that occurs, for example, when a sheet of material enters a magnetic field. It is perpendicular to the surface of the material provided. Kind of gave it away already. Well, what has to happen is charges have to be allowed to flow. Right? So that is all that is necessary. So that means you can have currents inside the sheet of metal, the so-called eddy currents. And these currents flowing, they then experience magnetic forces because they're moving charges, and that's what this braking force is. So it just has to be a conductor. Right. It doesn't have to be ferromagnetic. So even if you've got something like aluminum will not get attracted to a magnet. Right? Because doesn't have the same structure in terms of these magnetic domains that, say, an iron nail has on the inside. But it still allows, it's a conductor, so it allows for electrons to flow, so you can get things like eddy currents in them. Right? So ferromagnetic means that it gets attracted to a magnet, essentially. It gets magnetically polarized. But for say, eddy currents to flow, it only needs to be a conductor. Alright, let's go on to a couple more. So I've got a second list of questions here. Let's go through those. A coil of wire carrying a current may be used to create a magnetic field at the center of the coil. The radius of the coil is doubled, the number of windings and the current remain the same. And how does this change the strength of the magnetic field at the center? So in a sense, it's really just knowing what mathematical expression gives you the answer. And the answer is, let me type it out. So the magnetic field in this case is equal to mu naught, hard for me to write right in this basic text box here, can't write equations properly, mu naught times the current divided by this 2r, twice the radius. If I have a more than one winding, I just multiply this whole thing by n, the number of windings. And that just makes sense. Imagine I have 2 loops of current, well then I just get twice the magnetic field. It adds, right? So you just have how many windings, and then the magnetic field created by each winding. So in this case, we're told everything stays the same except I'm doubling r. Well, that means the magnetic field strength is half. But really, this is really about understanding, say, differences between what's a coil, what's a solenoid, creating magnetic fields versus being affected by a magnetic field. Right? Really, just keeping your concept straight. What this is about, and then therefore using the right equation for it. Okay, number 24. Which of the following constitutes an electromagnet? An object whose magnetic field may be turned on and off by electrical power supply. Let's go through them. 2 parallel plates, one carrying a positive and one other on a negative charge. Now that's a capacitor. Right, that is not an electromagnet, it's a capacitor. A long wire curled up into a spiral carrying current. That would function as an electromagnet. Right, because you turn the current on and off, and it's essentially a solenoid. What do you mean by long wire curled into a spiral? That is a solenoid. Right, so the answer seems to be B. Let's check the others. Large metal sphere carrying a positive or negative charge. No, that's just a charged sphere. It doesn't have any magnetic properties, right? It doesn't, the charges aren't moving. The battery suspended in conducting fluid, I don't know what would happen if you do that. I guess we just get a sort of current go through the fluid, nothing to do with the magnet. And if the current's strong enough, you might get some magnetic field there, but it's not an electromagnet. So the answer is B. Oops. Okay. 25, the last one of the multiple choice section. A sailboat with a vertical aluminum mast travels straight east along the equator at a constant speed. So visualize this, right? And think 3D, right? So if I look at it from above, I could draw north, south, west, east, and then I would look at the boat from above so that the mast would like stick out towards me. Or you can imagine drawing it from the side, in which case I might have the might have some water here, right? And then I'm going to draw my boat. Boat's going to be a box, right? I could draw my boat here, and then east would be to the right, right? This is east, and north is into the page because up is literally vertically up, right? So different ways you can visualize this from different directions. Just don't confuse north with vertically up. Right, so it travels through the Earth's magnetic field. Now, we've got to know which way the field points. Now, if we are at the equator, right, the magnetic field is essentially parallel to the ground. Again, this is something just to know because you understand the Earth's magnetic field, which is like a big bar magnet. If I look at it like this, with north up, east there, then the magnetic field would just be like this. Right. Whereas if I'm looking at it this way, now the magnetic field in this case, we're looking north, right? We're south of the boat, looking north. We watch the boat going east. But then the magnetic field is, pointing into the page, right? Because we're looking north. So now I've got a mast to my boat. Here it is, vertical mast. So what happens? The thing goes to the right, so right-hand rule, like point a thumb to the right, point the magnetic field into the page, so that your index finger along the magnetic field is into the page. So the force that you get from a middle finger is pointing upwards, but that's for positive charges. So negative charges, they want to go down, right? So I get positive charges gather here, and negative charges gather down here. Make sure it's really an application of the right-hand rule, right? To the mast, moving to the field, understanding that negative charges go the opposite direction. So the answer is D. But there can't be a continuous current because, I mean, like where would it be coming from? This is not a closed circuit of any kind, right? You just get an electric polarization because the mast ends here. You don't have a continuous supply of electrons. The answer is going to be D. All right, those were the multiple choice problems I was going to go through. Hopefully that helped. Maybe you tried them first; it would have been good. Or maybe you can now close this video and go through them all again to make sure you've actually understood what I was talking about. In the second video, I'm going to go through some long answer problems. I will see you there.